Yeah, thank you, and thank you, Paolo and Roberto, for getting us to this beautiful place and organizing this beautiful weather and the wonderful dinner. And I think we're all very happy that we came. So I will talk a little bit about the problem or our experiences with teaching or educating students that are ultimately going to work in the field at the interface between statistical physics and biology, which is an interface that is very active. I mean, we heard it from Eitan, an example yesterday. So many statistical physicists, as you will have noticed, have been going on into studying biological problems, and this, of course, needs to be reflected in the education to some extent. And so I thought to make this more concrete, I want to base this on what we're doing in Cologne. So this talk will have three parts. I will start speaking a little bit about the curriculum. I will then describe in somewhat more detail a specific course that I'm teaching that has and sort of emphasize the parallels between population genetics and statistical physics. And in the end, I will make some sort of broader remarks about the role of mathematics and biology and where we can go on from here. You will notice that those of you who know me, that my affiliation has changed somewhat. So this is part of what we're trying to do in Cologne to make biological physics a more visible and self-contained discipline. So we have reorganized the department now and have formed an Institute of Biological Physics. So the courses that I will be talking about are part of the Master of Science program at the University of Cologne. This is like in many other German universities. This is a research-oriented two-year study program. The aim is to get students into current research topics, and we have organized this around 7 what we call areas of specialization, which are general relativity and quantum field theory, astrophysics, experimental condensed matter physics, molecular physics, nuclear and particle physics, solid state theory and computational physics, and finally statistical and biological physics. In addition, there are further options that the students can choose at the University of Bonn, because we have a joint graduate school with the University of Bonn, which starts at the master's level. So all the master courses between Cologne and Bonn are sort of exchangeable. What is also important maybe in this context is that within this two-year study program, each student has to take one advanced theory course, and the choices are advanced quantum mechanics and advanced statistical physics. So there's an advanced statistical physics course that at least some fraction of the master students take. This is a fairly traditional course, I would say, in the sense that it's centered around critical phenomena and the randomization group. So that's the kind of thing that typically you would like students to learn in a second course of statistical physics. So I want to describe specifically what we're doing in this area of specialization on statistical and biological physics. And let me first tell you who is teaching this. So this is the faculty. So the Institute of Biological Physics consists of 5 full-time professors, 3 theorists, and 2 experimentalists. So Johannes Berg is a theorist who works on statistical physics methods of inference, in particular with applications to cancer. Tobias Bollenbach is an experimentalist who joined us a little bit less than 2 years ago, and who works on antibiotic resistance and microbial ecology. Gerhard Gomper is probably known to many of you. He's of course based in Jülich, but he's also part of the faculty in Cologne, yes?
Sorry, during the course of advanced statistical physics that you have mentioned is one of the 2 mandatory students. What is the starting topic, let's say, the starting level of this course?
Well, they all have bachelor degrees, so they have had an elementary course in statistical physics in the bachelor. So
example theory, we do statistical physics.
Yes, that they should know. So typically what we start with is phase transition. It's really very strongly based on phase transition. So we do phase transitions, Ising model, mean field theory, RG, and then typically in the end I also do a little bit of broader scale invariance out of equilibrium, but it's not mainly non-equilibrium. It's really equilibrium, and I think the core is really critical phenomena. Right, I mean, please interrupt me at any point if you have questions. So Gerhard Bromberg is in Munich, but he's also part of our institute, and his field is computational soft matter and biophysics. Michael Lessig and myself, we do statistical physics with various applications, specifically in evolutionary biology, population genetics, and quantitative biology. Veronique Meyer is a second experimentalist who does biophysics of bacterial systems. For example, she's worked a lot on bacterial motility. And then there are three more people who sort of contribute to this program. Andreas Schartschneider, whom many of you will know, works on non-equilibrium statistical physics, exclusion processes and traffic models. Matthias Sterl recently joined us. He's mainly based at the German Space Research Center in Köln and works on granular physics. And Dirk Witthaut is a young colleague also from Munich, who works on complex supply networks. Now this may seem like a lot of people, but of course one has to emphasize that there are only 5 people that are really core faculty. These colleagues who are associated with outside research centers, they of course teach much less. So they don't have to teach every semester. They typically teach like one course maybe every second semester. And so, as in every study program, the number of people involved in teaching of course poses certain limitations on what you can do. And that means that you cannot always give all the courses that you would like to offer to the students. So the curriculum in this statistical and biological physics program looks like this. So here we had to basically make a basic decision whether we wanted to make sure that all the students, because a student essentially only has 1 year for taking courses, right? So the first year of the master's program is when you take your courses, and whatever is offered during that year is what you can take. They can also take courses, of course, during the second year, but in the second year they really already should be working towards their master's thesis. And so we had to take a basic decision whether it was more important for us that everybody gets exposed to biological physics or, let's say, to non-equilibrium statistical physics, right? So both of these we cannot do. And so what we decided was to sort of put the biological physics part in the foreground. So we have a 2-semester course on biological physics, which is taught by the experimentalists, Veronique Meyer and Tobias Bollenbach. And then we have one theory course, which is called Evolutionary Biology and Genomics for Physicists, so all of these are sort of offered every year, so every student can take these courses. But of course, we also wanted, not to be the education to be too narrow. We wanted people that have taken a master's degree with us also to go on to work in other fields of statistical physics. So therefore, there's another course which is called Selected Topics in Statistical Physics, which is also, so one of these 3 courses is taught every year. One of them is non-equilibrium statistical physics, which is what I mentioned yesterday. When I teach it, there's a lot of KPZ and exclusion processes, but of course also some classical topics in non-equilibrium statistical physics. There's a course taught by Gerhard Bromberg on statistical physics of soft and biological matter, and a course taught by Johannes Berg, which is a combination of disordered systems and statistical physics of inference. And in addition, there are specialized courses that are taught more irregularly. For example, probability theory and stochastic processes, computational soft matter physics, network science. There's also something on granular physics. So this is essentially what we offer to the students. Of course, part of this is also, as in all other study programs, we also have to give students the opportunity to do their thesis in our field. And
how many courses do they take?
Excuse me?
How many courses do they take?
So this is, the credit system is fairly complicated, and it's, I think probably too complicated to be really useful, so we'll have to change this at some point. But essentially, if you have statistical and biological physics as your primary area of specialization, you have to take two so-called core courses. So all of these are core courses, so you have to take 2 of them. In addition, an advanced seminar and 1 specialized course. So that's,
do the students all come from physics bachelor or degree?
Yes, they all come from physics bachelors. Yeah. I mean, you know, we are open to students with other backgrounds. So also a biologist in principle could take this course, but we don't really target, and it doesn't happen very often. I mean, we don't target the courses towards this broader audience. So of course, students also do their thesis, and that includes also bachelor thesis. So of course, in the bachelor's program, students are not exposed to biological topics at all. Nevertheless, we do get requests, because all of us are also teaching in the bachelor program, we do get requests for thesis topics. So just to sort of give you an idea, so these are sort of examples of undergraduate thesis topics that I have supervised over the last couple of years. So 3 of those are BSc thesis, and it's not as difficult as you might think, because these topics that are largely, all of them I think, are related to population genetics. It's not that difficult to explain the basic structure of the model, and then, you know, so you can give the students, you can explain the model to the students, a little bit of context, and then often what they start doing is to write some simulation program, and then if they are good, they can, you know, they can try to get deeper into the problem also analytically. But it's sometimes they are a little bit scared, because they say, I know nothing about biology, and I would much prefer to do something in quantum mechanics. But once they get into it, I think most of them are fairly happy. So that I think works rather well. We don't need to give them that much background. And I think this is true of a lot of topics. I think also some of the examples that we've heard from the student presentations, like the surface growth talks, I think there's an advantage of our field that it's easy, you know, it's easy to write down a very simple model that you can study in an undergraduate thesis, already to the level of actually getting new results. I mean, it's not that difficult to, because I think in all of these projects, even in the bachelor thesis, the goal has always been to do something that is new, right? To get some result that is not done before. Okay, so let me now give you a little bit more detail about this specific course on evolutionary biology and genomics for physicists. So a kind of very short version of this is contained in a spring school lecture notes that I posted on the archive recently. So typically when I begin this course, I typically started with a short historical introduction, where I emphasize the close similarities in the historical development of genetics compared to statistical physics, which is something that is maybe not so widely known, but in some sense, in both fields, a very essential insight that largely occurred in the 19th century was about the discreteness of the basic constituents, right? So we heard about the atomic hypothesis in one of the student lectures yesterday, which was, of course, inferred in the 19th century by indirect means, largely from chemistry. You know, there was these sort of integer ratios that appeared, and then people like Boltzmann started, you know, taking this seriously. But there was a controversy, which, of course, as we all know, overshadowed Boltzmann's life to some extent. And similarly, in genetics, the crucial event was the discovery of Mendel's laws, which proved or which indicated that the hereditary material in organisms is discrete. And this was very important, because if this had not been the case, then Darwin's theory of evolution could never have worked. I mean, the key point about having discreteness at the genetic level is that it allows you to maintain variation. So if you have a population which have a broad range of genetic characters, and the individuals mate, because of the discreteness, they exchange the genes, but they don't reduce the variability in their properties, right? So you can maintain, this is what was later then formalized in terms of the Hardy-Weinberg law, you can maintain variation in random mating because the genes are discrete. Now in genetics, as I said, this was discovered by Mendel in 1865. Actually, Mendel for a while studied physics. I think he might even have studied with Boltzmann, who was in Vienna at this time. But unfortunately, Mendel's laws were not really, did not become mainstream knowledge at the time. They were largely forgotten, and they were rediscovered only around 1900. And at that point, so this is when people became aware of the discreteness of the genetic material. Now, at that point, again, a kind of controversy arose, very much like in statistical physics, in the sense that people thought that if it's true that there are these discrete genes, this must also mean that evolutionary changes are discrete, right? So you have a mutation, and suddenly your offspring is very different from yourself. Now, this is, of course, not what is typically happening, and this was not what Darwin described in his theory of evolution, because Darwin always emphasized that evolution acts in very small changes over very long periods of time. So this was considered to be a problem. So there was a controversy between the mutationalists who believed in big changes by mutations and the gradualists who believed in accumulation of small changes. And to reconcile these two points of view, very much like in statistical mechanics, what was needed was a statistical theory. Okay? And this statistical theory, this then led to what is now called the modern synthesis, and modern, it appeared in the 1930s, and it established population genetics as a mathematical theory, which I think with good evidence one can call the statistical mechanics of genes. And this is largely the work of these three gentlemen, Ronald Fisher, J.B.S. Haldane, and Sewell Wright, who established this theory in a couple of papers in the 1930s. And Sewell Wright has formulated this in one of his papers very beautifully, which I think is a good description of what it means, what collective phenomena are about, and I think also in the spirit of what John Philippe was telling us before. So what he's saying is that the problem that the evolutionary synthesis in some sense solves comes from the fact that people often fail to realize that the evolutionary process is concerned not with individuals but with the species, an intricate network of living matter, physically continuous in space-time, and with modes of response to external conditions which it appears can be related to the genetics of individuals only as a statistical consequence of the latter. So this is a complicated sentence, but what it expresses is that the evolutionary process is, of course, about changes in the genetic composition of populations. These changes, the elementary events driving these changes, are changes in the genetics of individuals, but they respond to external conditions and lead to, for example, to the adaptation of populations to their environment only in a statistical way. So in a statistical way, gene frequencies in populations change in such a way that the population becomes better adapted. But to sort of grasp that, you cannot do without a mathematical theory that is able to deal with large numbers in a statistical sense. Right? So in that sense, I think there is a very close analogy, and there is a very natural way in which you can apply statistical mechanics thinking to this field. And of course, still at this time, 1930, so 1930 was about the time when the Nobel Prize was given to Morgan for the theory of the gene, but still at this time, of course, the gene was still a hidden concept. I mean, I think at this point, probably in physics, everybody believed that there were atoms, thanks to especially Brownian motion, the experiments of Perrin, and so on. But around this time, you can still read comments saying that the gene is to the geneticist what the atom is to the physicist, just as no one has ever seen an atom, no one has ever seen a gene, right? So at this point, people didn't know what the molecular basis of heredity was. But nevertheless, the theory that these people formulated remains largely intact today. And now, of course, we know much more about the molecular details, but this still provides a very good framework. And I think that's sort of an important point, that the conceptual and mathematical framework in its broad outlines is largely in place. What has happened in recent decades is, of course, that there's been an avalanche of data, so our ability to collect detailed quantitative information about genetic changes has changed completely. and has brought the complexity of the interactions that are involved here into focus. Again, I think Eitan's talk gave some nice examples for that. And this is sort of where I see the role of physics, right? So we don't need to reinvent the field, but we can contribute our understanding of complex interactions to expand the framework in such a way that it can actually deal with the data that are coming out. Okay, so that's sort of the framework. Now the course outline is like this. So these are the things that I typically try to cover. So I start with a section on basic population dynamics. This is largely ordinary differential equations, logistic growth, a little bit of evolutionary game theory. We can talk about different equilibria, phase diagrams, and so on. And then there is an important part which is called genetic drift. So genetic drift in this context means stochastic effects, right? So these are stochastic effects that arise from the fact that populations are finite. This is of course requires, in terms of methods, knowledge of certain types of stochastic processes. And since we typically cannot expect students to have that knowledge, a lot of these concepts will be introduced within this framework, which is, I think, is good. I think you can introduce, and that's sort of one of my main points. I think you can use these kinds of models to introduce certain general concepts, just as you would, you can use a Brownian particle, you can use a random walk, but you can also use the Wright-Fisher or Moran model. I think these are just as good from a pedagogical point of view. Then there is a section about the way the genetic information is actually organized in terms of genetic sequences. And finally, there's a more specialized part which deals with a certain class of models which are known as quasi-species models. So I want to give you a little bit more detail on these parts. So let me start with a chapter on genetic drift. Okay. So one of the basic workhorses here is the so-called Wright-Fisher model. In its simplest version for asexual reproduction. So here the idea is that you have a population of n individuals. They reproduce in discrete time, and they have certain properties. So on this level, it's enough to know that each individual has a certain type. Okay, so we don't really need to say exactly what the type is. In this picture, the types are encoded by colors. And unless there is a mutation, so here this U is a mutation rate, unless there is a mutation, the type is transmitted to the offspring. Okay? The type comes with a certain property which is called fitness. Okay, so fitness is, in biological terms, a complicated concept, but here it just means it's the property that governs to what extent this type will be spreading in the population. And the way it governs this is very simple. So the way you can think about this is that you have one generation, you need to create the next generation. And so each individual in the new generation has to have a parent in the previous generation. And so you basically choose your parent backward in time, and you do that with a probability that is proportional to its fitness, right? So each of these guys has a fitness. You divide it by the sum of all the fitnesses, and that gives you the probability for drawing a backward link like this. Okay? And so here you see, for example, that this red type apparently, in a statistical sense, seems to be more successful than the other ones. And so at the end, the entire population is red. Novelty is introduced here through the mutations, right? So these mutations create new types. But if you don't have any mutations, then of course, in the long run, if you run this dynamics, irrespective of how you started, one of the types that are initially present will be the only one that is surviving, and that is of course an important part of this model. Okay. So if you formulate it in mathematical terms, you can say that each individual has a certain number of offspring in the new generation, which I call Ni, and then the basic definition of the model is in terms of the joint distribution of these offspring numbers, which is just multinomial sampling with these weights that are given by the fitness values. And another way of thinking about this is, which is maybe more realistic rather than this business of choosing parents backward in time, is that you start with Poisson distributed offspring numbers, and you condition the process on the total population size being constant, and then you end up with this formula. Okay, so that's sort of what you do. Now this is of course a fairly complicated process. Now to see what is going on, one can reduce it to just two types, and let's also to be even more simple, let's say the two types have the same fitness. So then it just means that you choose the new generation at random from the old one, and then you can, this reduces to a Markov chain on the numbers of individuals of one type, let's say type A, which is between 0 and capital N, and it has these binomial sampling rates, so you basically, the probability of going from n to n prime is given by this binomial coefficient times the frequency of a to the power n prime and the frequency of b to the power n minus n prime. So this is sort of the basic Markov chain. So at this point, you can sort of explain to the students what a Markov chain is. Yes?
Where do mutations come in here?
So here there are no mutations. So in the next couple of slides there will be no mutations. Okay, so I'm just mathematically speaking, it's interesting, or it turns out to be useful to know that this is a martingale, which means that the expected value of n prime given n is always n. Okay, so this means that if you start with a certain number of A individuals, on average this number will not change. Okay, now, and this is of course, and I think this is really the core of what genetic drift means. Of course, this is true on average, but of course, in any realization, as we have seen before, eventually you will end up having all A or all B, right? So every realization will end up being absorbed at one of the boundaries, but on average, the population doesn't change because it's a neutral situation where the fitness values are the same. And knowing that this is a martingale turns out to be useful in inducing some of the properties. Okay, so this is, as I already said, this Markov chain has absorbing states. So all A and all B are absorbing. And this is of course true generally as long as there are no mutations. So when a single mutant is introduced into a genetically homogeneous population, the outcome is either that it fixes, that is that all the types become mutated, or it goes extinct. Now, if there's no selection, so the case that we had here before, so in this neutral case, it's easy to see that the probability of fixation, so if I introduce one mutant, the probability that it fixes is 1 over n. This actually can be derived very elegantly using this martingale property. In the general case, computing the fixation probability for the Wright-Fisher model with unequal fitnesses is already beyond the reach of analytic methods. This is not something that one is really able to do. But one can do something in the limit when the population size becomes very large, because then you can basically, at least for the beginning of the process, you can ignore that the population size is finite, and then you can describe everything by a branching process. So at this point, you can introduce the concept of a branching process, and as you know, an important property of branching processes is that you can compute the asymptotic survival probability from this kind of implicit relation. And so this is now for the Wright-Fisher model also the fixation probability for an infinite, for a very large population, which is the solution of this equation. And when S, and so S is here now the so-called selection coefficient, so W prime over W, the ratio of the mutant fitness to the original fitness is 1 plus S. So when S is positive, the mutant is favored, and so the branching process is, as we would say, supercritical, so it has a finite probability of actually fixing, and this probability is given by this implicit relation. And then if you assume that S is also small, then you find that this is approximately 2S. So this is the famous result that was derived by Haldane, who basically also introduced this method of dealing with branching processes, at least in this context. So this is, so at this point you can talk about branching processes. Another way of dealing with fixation is to introduce a slightly different version of the model, which is called the Moran model. So the Moran model, in the Moran model, rather than replacing the entire population in each time step, you only replace one individual. So in one time step, one individual is chosen for replication and another is chosen at random for death. And this, of course, means that the number of mutants only changes by one in one time step. And so in the case of two types, the transition probabilities become much simpler, so you can only go from n to n plus 1 or from n to n minus 1. You always have this kind of logistic factor. And then you can easily compute the fixation probability. So if you start from n mutant individuals, the fixation probability can be computed in this way. So this is the fixation probability starting from n mutant individuals. So if you now, in the next step, make a transition from n to n plus 1, then from there on you again can go to fixation from n plus 1, or you do a transition from n to n minus 1 and go to fixation from there, or you do nothing and you stay where you are. So you have this recursion, and this recursion has boundary conditions. So if you start with 0 individuals, of course you cannot. If you start with capital N individuals, you fix with probability 1. So you have to solve this recursion with these boundary conditions, which is not very difficult, and you end up with this explicit formula for the fixation probability. Again, this computation can be simplified greatly if you discover that there is a sort of a version of this process that is still a martingale. And also what you can, and this is again something that you know, in terms of the general theory of stochastic processes that you can tell students at this point, which is that this fixation probability is an eigenvector of the adjoint of the time evolution operator. So in some sense what you're doing when you calculate the fixation probability, of course it's a kind of first passage or a splitting probability also, you're using the backwards time evolution operator. Okay, so now you have sort of explicit expressions for this. Now the next thing that you can do is to go to a kind of mesoscopic scale, right? I mean, we've heard a lot about Langevin equations here, and of course you can use Langevin equations here as well. So in this context, this is called the diffusion approximation, which was used a lot in particular by Kimura in his works on the neutral theory of evolution. So essentially, you know, you assume that the population size is large, but it's not infinite, right? So you go to a population size that is very large, but it's not infinite, so you still see the effect of fluctuations. And so on the Langevin level, this means that the frequency of mutants of small n over capital N satisfies this differential equation with the noise term. And the essential point is that the noise term is proportional to 1 over n. So you have a kind of you know, the noise strength is given by the inverse population size, and the Fokker-Planck equation that belongs to that. This is still without mutations, of course, so mutations will give you one more term. The Fokker-Planck equation that goes with that looks like this. So you have a diffusion term, which has a scale 1 over n, and you have now what we would call a drift term or a deterministic term that has the selection coefficient in front of it. And of course, this still contains the absorbing states. So for example, if you try to find the stationary solution of this equation, you will find that it's not normalizable. And this is of course because as time goes on under this process, you know, all trajectories eventually get stuck at 0 or 1. Okay, so the stationary distribution is strictly speaking a sum of 2 delta peaks. And again, you can calculate the fixation probabilities by using the backwards equation. So you just do the adjoint of this operator, and you look for an eigenfunction of that, and that's where you get the fixation probabilities. Now, what is important about this is that this is, of course, a kind of central limit type argument. So this diffusion formulation is universal in the same way that, say, the KPZ equation is a universal description of certain microscopic models. So it holds also for the Moran model, and in fact it holds for any microscopic model that has a finite variance offspring distribution. And now if you don't, of course, and here, you know, I typically don't have time for that, but at this point, of course, you can start talking about cases where the offspring distribution doesn't have a finite variance, and what happens then. And this is in particular interesting also for the backwards genealogical process, which I don't have time to talk about here, but which would then be like the next step in this discussion. So if you, instead of looking at the population as it evolves forward in time, if you pick some subset of individuals and you want to know how they are related backwards in time, so you want to know where their common ancestors are, this is governed by a stochastic process on partitions, which is called Kingman's coalescence. So this was introduced in 1982. And it's again a universal object, just like the diffusion approximation is a universal object. It's a universal stochastic process that applies to all models that have a finite variance offspring distribution, and extending this to offspring distributions that have infinite variance is a whole industry in mathematical biology, which is associated with various extensions of this coalescent approach. Now, one thing that I think is interesting from the point of view of physicists is that also the concept of detailed balance appears here, and this is actually something that was discovered, as far as I know, remarkably late. So as far as I know, this was first pointed out by Michael Lessig and collaborators, and independently by Sella and Hirsch. And so at this point we sort of introduce mutations in a weak way. So we look at a weak mutation regime. So suppose so far what I've been telling you so far is that, maybe let me just go back to the beginning. So what I told you so far is that if there are no mutations, after a certain time the population will be genetically homogeneous, right? So everybody will have the same type. Now if we now introduce a little bit of mutations, then typically what will happen is that the population is genetically homogeneous. Once in a while a mutant will come up, right? So a mutant will appear, and then it either goes to fixation or it goes to extinct. If it goes to fixation, this means that the entire population now adopts this new type, right? So that's sort of the weak mutation regime. And so when these mutations are very rare, the population simply evolves through single fixation events. And so now with that we can define the Markov chain not on the space of the number of mutants, but on the type space, where the transition rate to go from type A to B up to the rate, which is just the mutation rate, is equal to the fixation probability. Right? So the probability of going from A to B is the probability that the B mutant fixes in the background of A. And the key observation now is that, at least for the Moran model, and for certain other approximations that you can make, that this Markov chain is reversible, and it has a stationary distribution that has a very simple shape. Okay, so for the Moran model, you can do a simple computation and see that the probability, the stationary probability of having type A is just the fitness of A to the power n minus 1. And this is also true for the fixation probability of that you would get in the diffusion approximation. As far as I know, it's not known if it's actually true for the full Wright-Fisher model. So this is something that that I still think one should probably investigate. So it's not clear to me whether this is a coincidence or whether it really means something deep. But of course, from the physical point of view, you can see that this is like a Boltzmann distribution. So you can say that the equilibrium state of the population in such a regime, so that if you have a finite type space, you run the thing long enough. It will go to a stationary distribution where the probability of finding a certain type is a thermal distribution with energy log W and an inverse temperature, which is essentially the population size. And of course, based on this, you can now do statistical mechanics. In a practical sense, this is important because it means that, at least under appropriate conditions, you can infer empirically fitness from abundance, right? So if you just see how frequently you see a certain sequence of a transcription factor, for example, you can infer its fitness, or at least you can infer the product of fitness and population size. But you can also elaborate on that. For example, you can now assume that fitness landscapes that the fitnesses are somehow time dependent, and then you can do things of the type that Udo was telling us about 2 days ago, and derive fluctuation theorems, for example, for quantities related to fitness. Okay, so that's sort of the story having to do with these stochastic population models. The other big topic where there are interesting connections to physics is this chapter about sequence space and fitness landscape. So here the idea is simply, so at this, in this whole part, I haven't really talked about what the types are, right? So, and this is of course for many applications, this is not that important. I mean, you have some situation where you have some mutations that appear in the population, and you want to say something about the probability of fixation. But of course, ultimately, we know that the types are encoded in sequences, as Eitan was explaining to us yesterday in the DNA sequences. And so the structure of the space obviously has to be important. And this was, of course, also realized by the founding fathers of the field. So the notion of a fitness landscape was introduced by Sewell Wright already in 1932, and these are pictures from his original paper. As I said, at the time it was not, people didn't really know anything about the structure of the DNA, but what they did know was that there were discrete entities, genes, which could appear in different versions. So a gene would have different, what we call alleles, right? So a gene could appear in different versions in different organisms. And so, so suppose now that you have two genes, you have, this cross is the so-called wild type, so this is sort of the original type, and then you can have a mutation at one locus which gives you a B, and you have a mutation at another locus which gives you an A, and then you have the double mutant AB. So this would be the sequence space of a binary sequence of length 2. This is the sequence space of a binary sequence of length 3, right? So here you have ABC, triple mutant, and so on. So these are the state spaces of a binary mutation model on a finite number of loci. These are, mathematically speaking, these are hypercubes, as you can see, right? There's a cube, this is a 4-dimensional cube, this is a 5-dimensional cube. And the idea of the fitness landscape is simply to say, okay, these are my types, so I have to assign a fitness value to each of these types, right? And apparently when Wright wrote this paper, the editor of these conference proceedings told him, well, this is too complicated, our readers will not be able to understand this, you have to visualize your concept in a simpler way. And so he also added this picture, where now this discrete hypercube is sort of represented by a 2-dimensional plane, and then you can, of course, plot the fitness as a third coordinate, and this is now a topographic map where the fitness peaks are pluses and the fitness values are minuses. And Wright writes already in his paper that this is a very inadequate representation of the concept. I mean, obviously, this is what you really have. You have this high-dimensional discrete space. You don't have a low-dimensional Euclidean space. But in some sense, this was the picture that survived. So if you look at most textbooks in evolutionary biology, you will always find a picture like this. And then the picture of adaptation, of course, is that a population is a point in this space that sort of moves towards higher fitness, or populations are sort of moving up here and trying to cross values and so on.
What are the ordinate and abscissa on that graph?
Sorry?
I'm here.
Yeah.
The ordinate and abscissa, what are they?
Here?
Yes.
Yeah, well, that's the problem. I mean, one doesn't really know, right? I mean, I would say, so of course, I think the more sensible way, if you want to think about Euclidean spaces, you probably want to draw some phenotypes here, right? So you could put some expression levels or something of the kind that Eitan was talking about. But of course, you cannot really project this space onto that plane, right? So this is, in that sense, this is a purely metaphorical picture. And this is still the way it sort of appears in most papers, right? So this is a picture from some fairly recent paper discussing different evolutionary trajectories. So the picture is always your population starts somewhere and then it sort of moves up, and maybe there are sort of different peaks that it can reach and so on. So it's used in this metaphorical sense. But what has happened over the last 10 years or so is that the underlying, the proper underlying sequence-based picture has become much more mainstream. And I think this is, a lot of this was triggered by a seminal paper by Jan Weinreich and collaborators in 2006 who applied this concept to antibiotic resistance evolution. So this is essentially, so I don't really have time to go into detail about this, but what he was interested in was the evolution of antibiotic resistance in a certain enzyme, the so-called 10-1 beta-lactamase, and there was a 5-fold mutant of very high resistance that evolved from a wild type of very low resistance over 5 mutations. And Weinreich was interested in the possible pathways that one could along which this could evolve. And so he constructed all the intermediates. So if you have 5 mutations, you have 2 to the 5 possible sequences, 32 different enzymes, which he manufactured, and then he measured their resistance, and he found that only a few pathways were such that resistance would increase in every step. Okay? And this really has led now to big development. A lot of people have been studying similar landscapes, also on larger scales. And I think it's not a coincidence that Weinreich actually has a computer science background. So he got an undergraduate degree in computer science. He worked in the software industry for about 10 years. And then he went back to the university and decided to get a PhD in biology. And he's now a professor at Brown. But I think, so his way of thinking clearly, made it easier for him to actually explore this, which basically hadn't been done before at all. And this is now quite an industry. So this is an early picture from our own work, collaboration with Ariane de Visser on a fitness landscape of a fungus. And this is just the way we like to represent these things. So this is now a 5-dimensional fitness landscape, a 5-dimensional hypercube, and we draw arrows in the direction of increasing fitness, and then you can sort of analyze things like local peaks. So these are sequences where all the arrows come in, and you can ask how likely is it to evolve from one place to another. Now, what does this have to do with statistical physics? Well, essentially, of course, we're looking at complicated functions on hypercubes, and of course, for a physicist, the hypercube is really the state space of an isomorph, right? So if you have binary sequences, you can represent them by spin variables, and then you can represent any function like this. You can represent as an expansion over terms containing products of spins that come from subsets of the total number of spins, which I call L here. And there's a kind of interesting, there's sort of 2 versions of this. I think I probably shouldn't say too much about that, but you can, so in population dynamics, typically people like to use zeros and ones. From a physics point of view, one would like to use minus ones and ones. And these are called in a notation going back to Ed Weinberger, these are sometimes called Taylor and Fourier expansions, and the difference between the two is not entirely trivial. In particular, if you choose the minus ones and ones, what you're actually doing is an expansion in orthogonal eigenfunction of the graph Laplacian, and this has certain orthogonal properties that are nice, so this is sort of what we're trying to advocate now. But generally, this provides a kind of framework for analyzing these kinds of fitness landscapes. And of course, if you now want to model this from a statistical physics point of view, the obvious thing that you would like to do is to write down a function like this with some sort of random coefficients. And so there is a lot of interest now in these probabilistic models of fitness landscapes. We recently wrote a review on one of the most commonly used models, the NK model in the Journal of Statistical Physics. And these serve in different roles. They serve the role of parametrizing empirical data sets, but also to understand how things, what these landscapes look like when you have very large, very long sequences, so to sort of extrapolate, if it's possible at all, from small samples to genome-wide scales. The early development here, which goes back very much to Stuart Kaufman, of course, was strongly influenced by spin glass theory. So if you go back to these papers, like especially Kaufman and Weinberger, 89, you find that there are constant references to spin glass work. And so now the kind of theoretical questions that we ask in this field are very similar to those that you would ask in the statistical mechanics of disordered systems. One is interested in the number of local fitness peaks, which translates into properties of metastable states in the spin glass context. One is interested in the difference between typical and average properties, and of course in the accessibility of high fitness genotypes by different types of dynamics. But one has to keep in mind that this analogy is very close as long as you're in this weak mutation regime where the entire population is sort of described by the same configuration. But if you go beyond that, then the analogy is not that close anymore. Okay, so if I have a few more minutes.
Yeah.
So let me then just give you a few kind of summary remarks. Now, part of what we're of course doing is trying to use mathematics to understand problems in evolutionary biology. And so one can ask more generally, what is the use of mathematics in biology? And I think this is sort of an important question because it's not in physics, nobody would ask this question, right? I mean, physics, I think physics over the last 300 years has been a success story of the application of mathematics. Now in biology, you still have a lot of people who say, we don't need this, right? Or the systems are too complicated, you will not be able to make any sense. Now, what is the role? So one sort of basic role, if you talk to experimentalists, and this is, I think, also in the spirit of what Eitan was saying yesterday, is that mathematics is a way of making sense of data. Okay, so you have some data, you arrange them in some way, and you try to find patterns. This is, of course, very basic, but I think it's maybe not even the most important role. I think another important role is understanding the emergence of complexity, and this refers, I think, also to what Jean-Philippe was saying, that mathematical models can help you to understand how complexity can arise from simple components, and this was already clear to Haldane. So he says here, non-mathematicians often fail to realize the complexity of behavior and sometimes the self-regulatory capacity of material systems composed of simple components. So this is, I think, something that a role that physicists in particular have to play here. And finally, I think what is also important is what I would call providing abstract imagination. So this is a long quotation from Ronald Fisher. So he says, what is profoundly susceptible of training is imagination, and mathematicians and biologists, and I think you could also write physicists here, seem to differ enormously in the manner in which their imaginations are employed. No practical biologist interested in sexual reproduction would be led to work out the detailed consequences experienced by organisms having 3 or more sexes. Yet what else should he do if he wishes to understand why the sexes are in fact always 2? So this is, of course, a very important way of going about things, that you have to be able to imagine that things could be different. And in fact, I mean, this is from 1930. With hindsight, this is of course not true. There are organisms with all kinds of numbers of sexes, so it's not as simple. But of course, there is a kind of, there is a preference for 2 sexes. Well, what is the state of this field? So I think what you can see is that there's a kind of coherent community that is emerging at the interface of statistical physics, evolutionary biology, and population genetics. The ingredients are developing these concepts that I have explained. An important role is played by experimental evolution with microbial populations, which I haven't really gone into, and also with medical applications. So we heard from Eitan an example, and this seems to be a general trend that people try to apply their concepts to medical problems. There are signs of establishment in the sense that at various places cross-disciplinary institutions are being set up. There are these regular long-term programs, for example, at the KIDP and in other places. But I think it's still, you know, the community is there, but it's still not established in all respects. For example, it's still a problem to figure out where to publish this stuff, right? So we try to publish a lot in genetics and biology journals, but this has certain disadvantages because the way you treat mathematical parts of the paper is not like in physics. On the other hand, if you publish it in physics, no biologist will read it. So this is still something that I think could be improved. There are some challenges in terms of research. So there's something that is, you know, that I broadly call here the problem of scale. So of course the sampling of the space of genotypes is always very sparse. And I think an important issue here is the heterogeneity of biological systems. So what I say here is that in biological systems, the heterogeneity is functional rather than statistical. So what we're sort of used to is being able to coarse grain, right? Now, of course, in a magnet, you know, you have the spins, and then you maybe have the domains, and you have the whole system. So it's a relatively, you know, of course, things sort of change from one scale to the other, but they don't change in a very fundamental way. And in biology, one also has the feeling that the heterogeneity is such that you cannot really coarse grain, or you have to impose a lot of previous knowledge in order to be able to do that. There is an issue of the genotype-phenotype fitness maps, time-dependent environments, and I think also one thing that is very far away is to really understand true novelty. I mean, what we're beginning to understand in a kind of quantitative way are changes like the increase of antibiotic resistance or the increase of growth rates in some bacteria. But of course, all of these are very, you know, innocuous changes compared to you know, the invention of flight or the invention of the eye or something like that. So I think this is still, there's a long way to go. In terms of teaching, as I said in the beginning, what we want to do is to provide students with a solid grounding in modern statistical physics, while at the same time introducing them to biological concepts. And I think the way to do that is to introduce biological topics at an earlier stage. So I think even in a basic statistical mechanics course, you could describe, say, the Moran model as an example of a Markov chain and a detailed balance and so on. Now there are of course skills that are needed to work in this field that are not typically conveyed in the physics course, in particular statistical and computational tools. To me, it's very ironical that as a statistical physicist, I always have to tell my biological collaborators that I have no idea of statistics, right? I know nothing about p-values and chi-square tests and all that stuff. So this is, now the students can learn this, and one way of doing that is, of course, is to have them take bioinformatics courses, and also, of course, by simply doing the work. And a somewhat separate problem is how to communicate these things to biologists who typically don't have the mathematical background, who might even have difficulty understanding differential equations. I think this is hard, but I think one thing that I found useful is to actually try it and teach summer schools to mixed audiences, and there you sort of learn to try to break down your models to their essentials, and also to develop pictorial representations for a lot of things that you usually would represent mathematically. Okay, so I think at this point I should stop. So let me just finish with a quotation. You know, you could ask, why bother? I mean, why should you make this effort to work in biology? So this is a quotation that I found a few weeks ago from the current director of the Santa Fe Institute, David Krakauer, who says that physics always seemed rather obvious to me, the universe of particles, forces, and fields. The living world is so much messier and odder and frankly incomprehensible. So I think this is what is sort of driving us. Thank you very much.
Thank you very much. Question?
Yes. Can you take your evolution scale with the color? Mm-hmm. The question is, how there is the influence of environment for changing the gene, for gene mutation? This is the question.
No, there's no environment here really. I mean, these mutations are random. The only, you could of course also ask why do you insist on keeping the population size constant. This is of course not very realistic, but it's a way it's sort of a mathematically convenient way. It's clear that the population size is important in governing the population.
Because the environment always...
And the environment, in some sense, will control the population size. So in that sense, yeah.
My question is related to this, okay. For physicists, the determinism was died because after chaos and other development. In genetics, okay, in 2000, all people believe we know human genome, then we can know everything. It's false because there is epigenetic. Epigenetics say that we should take into account the environment which change all the time. So just a comment from you. Then a comment from you because I have done some work in collaboration with biologists. Or quantitative biologists means the model is just a simple relation between some quantity. They put random some coefficient, make calculation, they change again, make calculation, just by hand. So this field can be, this interdisciplinary field can be very interesting to develop how the physicists make models. For clever biologists, can be very interesting because there are, okay, my work is this, physics, that doesn't matter. But for very clever, the research field could be very interesting. Just my comment.
Yeah, I mean, I think, of course, I think Eitan made this nice comment yesterday. What is the defining feature of physicists getting into this field is their arrogance. Now, so he meant this in a positive way, but I think one has to be. So my view here has been that at least I want to start with something that is established in biology, right? So the Wright-Fisher model, the boron model, this is something that people have worked with for decades. So if I say this is what I'm going to use, they are happy. Of course, you could say, as a physicist, I think this is not a good model, and I want to change it. And of course, you do that to some extent, but I think it's always important to keep within the range of the discipline in order to, because otherwise people will at some point not listen to you anymore. And Daniel Fisher makes this nice statement. I mean, he also works in this field, and he likes always to say all models are wrong, but some models are useful, right? So that's, and in biology, I think this is more true than in physics. I mean, also, of course, in physics, all models are wrong to some extent, but in biology, they're typically wrong to a larger extent. But some of them are useful, and some of them are, familiar to people, and I think that's certainly an advantage.
Okay, so I think John. No, question.
Okay. I quite agree. Just first comment. I quite agree with the last things you were mentioning. That it's important to take care also how to teach these things to a wider audience of people. And probably the idea of some schools or spring schools are very, or summer schools are very interesting to be pursued up to the end and try to transmit common information. I agree that arrogance is important in the positive sense of Eitan, but we must be as a community of physicists open to the language and the knowledge of the others. So there might be a sort of, clear exchange between these fields. And this happens at any level, I think, not only in genetics, but in neurosciences or any kind of application. Probably in social sciences do the same. There's a general statement, and probably organizing schools where people have the cultural open-mindedness to make that together, and coming from different disciplines would be probably a good, scheme to work out such a school. On the other hand, I have some specific comments about genetics. You see, I'm a bit concerned by the certain tendencies that nowadays appear, because it's clear that there is this big data, approach, that you have a lot of genomes that are being stored, and you can understand much more. And this is, in some sense, in my opinion, a cultural problem, because it renews the idea that sort of determinism can drive you to know much more about something. This is partly true, because it's clear that if you have some amount of information that may be extremely helpful to understand more, and sometimes it's clear that you have more than many more human genomes to compare, probably you can learn something. But on the other hand, it's not just, in my opinion, it's not just a matter of organizing this information, but also to have models to understand the information. And this is to me a message, a cultural message that concerns also teaching, but in my opinion, maybe I'm wrong, but the feeling that this approach is minority.
Yeah.
So I think that most people believe that this data mining or the way of increasing the amount of data rather having suitable models to understand this is important. And when I address certain questions to people like biologists, I would like really to be arrogant in some cases, because I would like to have some answers. I know that I cannot get answers to certain questions, but I would like that these people could think about certain problems. For instance, why the human genome is 3% coding, while in bacteria you have almost 35% coding. There are reasons for that. When you pose this question to a biologist, for him it's obvious. But if you look at this problem from the point of view of statistical approach, this is totally unobvious. So,
yeah, I think there is a difference in terms of what it means to understand something.
Yeah.
Right? I think for us we have a certain way of thinking that there has to be a model that is sufficiently simple to sort of think through, and then if you have such a model that fits the data, then you say you have understood something. But of course, and I think it's not clear. I think with a new development in terms of data mining, deep learning, and so on, this point of view could just go extinct. I think it's because I think a lot of biologists, for them, understanding means knowing what genes are responsible, right? So you have this haystack of stuff, and you run it through your algorithms, and in the end it points you to a particular gene, and then you test that. And if that is confirmed, you knock out the gene, the phenomenon disappears, and then you say, I've understood it, right? And this is, of course, to us this would be unsatisfactory, but I think the jury is still out on which point of view will in the end prevail, and I think this actually concerns even physics, because also in quantum many-body theory, people are now very excited about deep learning, and they have trained neural networks to find ground states of complicated quantum magnets and so on. And so it might be that people who believe in models will eventually be out of business, but okay, I hope not. But I think it's not clear.
I would thank again the speakers of this morning.